Okay. Let's see. I am on. So, so Marios, thank you very much, and thank you all for having me here. It's really an honor. I am not your new athletic director, but I'm thinking about applying since I hear the job is open. Sure. So it's hard to know always what to talk about here. My life nowadays does involve a lot of public speaking and lecturing, and typically those are of one of two types. I give what are mostly marketing talks to customers and other partners for Microsoft, and then I give academic lectures, usually on technical topics. This type of talk is a little bit different, and so I thought just to dive in, what I would do is, first of all, start a little bit about my own background and how I got into research. And the reason I want to do that is with the hopes that maybe some of you students here might also develop an interest in a research career. And let's see how that goes. So let me start with this image. For me, this image represents my childhood. So this is from the Houghton County Road Commission. And this is a picture from the town of Houghton, Michigan, which is 550 or so miles north of here. And that's where I grew up. And the snow, of course, is particularly important because my father was a physics professor and researcher at Michigan Tech, and my mom a chemistry professor. And my father, his research in particular was the physics of lattice and crystalline structures applied specifically to the properties of snow. And so he was one of the world's preeminent experts in snow. And so Houghton was a very good place to be. In fact, some of the turbine blades for snowplows and snowblowers like that were designed by my father. Now, I want you to imagine growing up in a small town in Upper Michigan, in an Asian household, with a father as a physics professor and a mother as a chemistry professor. And so you must realize that there is no chance that I would be anything but a scientist of some kind. And so here I am. And in fact, it was a very important thing for me growing up in that household, and really a very serious physical science household. Now, it turns out, even though this was a long, long time ago. I was born in 1960, and so computers were very, very new and a nascent idea. I did get some exposure to computers in high school and became very much attracted to computers and computing in general. And in fact, that interest was pretty profound, and I thought that maybe I would go to school to study this. But of course, from my parents' perspective, computing was not, it's the old joke, any field that has science in its title can't actually be a real science. And so there was just a very hard push away from computer science as a discipline to pursue in college. And so I started off life here at the University of Michigan as a physics professor, and as a physics student and major. Yeah. And that tenure as a physics major lasted until I got into thermodynamics, at which point I realized that physics is very hard, and I switched to mathematics. And so still a tremendous disappointment, I'm sure, to my parents. And throughout all of this, it became increasingly apparent that I was really, really, really in love with computing. And I'll try to explain a little bit later why I think computing is so important and why I think it is, in fact, maybe the most important intellectual endeavor of our age. But it was a slow process for me to just become convinced that it was actually a legitimate thing to study. Now, one of the things that happened that was very important is in in between the junior and senior years here at Michigan, I had a chance, I ran into a professor, Uwe Plebun, and he exposed me to the research work coming out of Oxford University by this man, Dana Scott. And Dana was doing very theoretical research. In fact, it was research that was really only being done in the United Kingdom at the time. Of course, his style of research is now very common in the US, but at the time, it was very unusual in the US. And in it, he was really trying to understand the nature of computation in mathematical terms. Really, up until this point, the dominant thinking around computing was either in the hardware and in the circuitry, and all of the phenomena around the circuitry, or in programs and programming. And there was very little outside of, say, computability and complexity theory that was a focus of mathematics when applied to computing. But Dana was doing some very, very interesting work. And I know not everyone here is a computer scientist or an engineer and a computer programmer, but I'm going to show you a couple of things. I have one slide of semi-technical stuff, just to give you an idea of what attracted me to Dana's work. So I'm going to start with this thing. If you're familiar with computer programming, I think you can read this and instantly recognize this as a computer program, and a computer program which calculates the factorial of its input. But if you have that mindset, I want you to put that aside and just think like a mathematician. And if you think like a mathematician, this is not a computer program. This is simply a mathematical equation. And in fact, as a mathematician, this is an equation that is a math problem, namely, solve for f. Okay? And so you want to find a value for f such that this equation holds. And a little bit of thought would tell you that if you have God's factorial function, so God gives you the factorial function, whatever that is, and you plug that in for f into the equation is satisfied. And so it's no big deal. So from the perspective, maybe all the way from the 1940s through the entire 1950s, mathematicians who thought about computing really viewed computing as just mathematics, really nothing more than that. And relative to the perspective that I grew up with in my household with a physics professor, dad, and a chemistry professor, mom, this is also an indication that there was really nothing new in the intellectual pursuit of computing. Nothing new in computer science. But what was remarkable about the work of Dana Scott is that he had the insight that there was no mathematics of the time, at least not in 1960, that it could account for equations like this. And one way to see that, it's very technical, but one easy way to see that is to look at other equations. And so if you look at this equation at the bottom of this slide, again, if you're a computer programmer, you will recognize that this is not a program. It does not compute anything. And yet, the factorial function, when plugged in for f, solves the equation. And in fact, in 1960, before the work of Dana Scott, there was actually no mathematics that could account for this difference. No mathematics prior to 1960 that could separate what is clearly not a program, not a sensible program from a computer science perspective, from a clear and easy solution from a mathematics perspective. And Dana's insight just started to completely destroy the conventional mathematical thinking around computation of the time, and actually led to a whole new science of what became the computer science field of formal semantics. Now, for me, this kind of insight was just incredibly, incredibly beautiful. It kind of gave me the license to realize there was something really new and intellectually deep and important in computer science study, and it kind of gave me the top cover to stop feeling embarrassed about being in love with computer science. And so I ended up finishing a degree here in computer science, computer and communication sciences, and then going on to graduate school to study the same. And so that was my undergrad career. I ended up staying for graduate school. I had a one-year stint working on a startup, finished my degree. I show this picture of the Nichols Arcade because in the Nichols Arcade I finished my PhD. I wrote a good dissertation here. I ended up having 23 job interviews everywhere, and in that process at Boersma Travel, which doesn't exist anymore, I met my wife. And so everything was all set. It was all great. So I had a PhD and a wife to boot, which is great. So after that, then I went as Mario's explained, I took up a faculty position at Carnegie Mellon University, and this is a picture of the Gates building at Carnegie Mellon. And I went there because about 3 years before I finished my PhD, Carnegie Mellon managed to hire Dana Scott away from Oxford. And so he was such a tremendous influence on me, I went to work with Dana at Carnegie Mellon. And at Carnegie Mellon, I continued this very theoretical work that just really had some crystalline beauty to it, I felt. And in fact, this is an image from a research paper that I wrote in 1996 on the topic of proof-carrying code, which helped elevate me to the position of full professor at Carnegie Mellon. And I don't expect this to make any sense to anyone, but I just want to give you a sense of how kind of full of Greek and how theoretical the work was. And it was really a work that was really devoted to serious beauty. So now I was very happy there, and then the department head who hired me at Carnegie Mellon, Nico Haberman, unfortunately passed away very suddenly from a heart attack. And the new department head came, and as a new department head would do, he had one-on-one meetings with all the faculty members to just talk about what work they were doing. And I explained my work, and I explained just how beautiful I thought this was. And unfortunately, and this was before I had tenure, the department head said, Peter, I don't know why you're doing this work. I just don't see any value in it. And I, of course, was very nervous hearing that. And then he kept pressing me, why are you doing this work? And I said, the only thing that I could say, which is, I said, it's just so beautiful. To which he said, if you think that beauty is so important, maybe you should go be a professor in the fine arts school. And this was just really kind of a devastating thing to hear. But also, as I think about my career, something that is very important. And I tell this story actually to people who come to join us in Microsoft Research. There are often times when if you're doing something very important and potentially disruptive, when the world really doubts you. And in fact, if you think about the nature of technological disruption, if the things that you're doing don't provoke people, don't provoke their doubts, and don't provoke their skepticism, then probably you have a very low chance of surprising them with the results. It could be possible that what you're doing is completely stupid. But it's also a possibility that what you're doing, if not stupid, could be completely disruptive and surprising. Because the nature of disruption involves a level of surprise, involves initial element of doubt. And so for me, working through the doubts of my then new department head, and actually ultimately developing a very close relationship with him that ended up being very productive and very positive, was an important turning point. And so there's a level of independence that I think if you think you have, then is an important reason to consider a career in research. And incidentally, with respect to my work, one of the proudest moments of my career was learning that some of the fundamental concepts developed in my research Carnegie Mellon is now deployed in very large data centers at Microsoft, churning away, doing automatic program analysis and proving through SMT proving over 200 million theorems automatically and symbolically every day, searching for and finding serious high priority bugs in Microsoft Windows and Microsoft Office applications. And so, in fact, I think it's true that one of the wonderful things about computing is that oftentimes the most beautiful things that we do, the most beautiful solutions to problems, also end up being the most practical ones. All right, so enough about that background. I now want to just talk more generally about computing research and what's, I think, important about it. And to do this, what I thought I would do is take one moment in history, the world's history, to talk about research and computing research. And so, for those of you that don't recognize this is a photograph of Neil Armstrong in 1969 on the first day that man set foot on the moon. And so it's really a famous photograph. And if you think about this, I don't know if you can really, if you're not old like the faculty and I am, if you're not quite, if you haven't lived through it, if you can really grasp just how monumental this was. Now, from the day the project started, 50,000 people were mobilized to all work together to achieve within 9 years putting a man on the moon and getting him back to Earth. It was just really incredible. And if you think about it in today's world, you can actually wonder, would that be possible today? Would we be able to mobilize such a force of people to collaboratively work together and put a man on the moon in less than a decade? And we did that in the 1960s. Pretty amazing. And there were incredible discoveries that were made, stupendously hard technological and scientific problems that had to be solved, and a lot of spin-off technologies. And for me, this was really fundamental. I really was just 9 years old, actually 8 years old, watching this on TV every day. And I was eating space food sticks and drinking Tang. I know most of you don't know what that is, but people were selling junk food, saying that the astronauts were eating it. And so I was doing all of that, and it was really pretty amazing. And I think part of my inspiration to become associated with technology was inspired by this. Now, of course, that's not all that happened in 1969. In that same year was another monumental achievement in science and technology, because in 1969 was also the year the ARPANET was invented and deployed. So initially, early in the year, in the summer, in 1969, the first 2 nodes of the ARPANET that eventually became the internet, one node at UCLA, the other node at the Stanford Research Institute. And the first message was sent from Los Angeles to Palo Alto. There was an attempt to send the word login, but after L and O, there was a buffer overflow, the world's first buffer overflow. And the system crashed. And then later in the year, 2 additional nodes were added, and there were 4 nodes of the ARPANET. And in that ARPANET, there was a demonstration by a researcher and a research group at Stanford Research Institute led by Doug Engelbart that is sometimes referred to in computer science circles as the mother of all demos. And so to try to express how remarkable this demo was, you have to remember that when the ARPANET was created, it was created and conceived primarily as a reliable communications network. The Cold War was in full swing. The threat of nuclear annihilation was very real and visceral in the world. And there was a real national security mandate to create a military communications network that could survive and adapt to the severe damage that might take place during a war. And in that context, it's remarkable that there was already the thought process that such a network might be useful for more than just giving reliable communications. That an internetwork might also enable people who are separated through time and space to usefully collaborate. together. And so this mother of all demos showed how two people, one person in Utah and one person in Palo Alto, could collaborate in the construction of a document. And just an amazing thing. And you can see talking about the human feel for a situation. And new interface ideas like the mouse were invented for this demonstration. So you see this very quaint, the first computer mouse there, carved out of wood. So think about it, 1969, these two things. And in fact, in my mind, 1969 is the greatest year in human history for technological advancement, just on the basis of these two things happening in that year. So now, as we look back over those 45 years, from then to now, I want to ask a rhetorical question. Of those two things, which one of these two achievements in '69 had greater impact? And it's a silly question, rhetorical question, because in a way they're both incredibly important. I mean, heck, we have Velcro now because of the moon landing. But the way I have answered this question in the past is to ask another rhetorical question. And I know most of you aren't parents, but imagine that you are. So Sue and I have a 17-year-old son, and he has never used Saturn V booster technology to reinforce his math homework. And so he's probably also never used lunar lander technology to download porn behind our backs. But the point here is that computing technology is incredibly important and powerful because it can be so readily democratized. In fact, there has been no greater force for technological democratization than computing technology. And when you put incredibly powerful tools in the hands of so many people, you're guaranteed to get a constant stream of great innovations. And what we have seen over the past 45 years is exactly that out of computing technology. And there's just really no end in sight for this right now. Just think, if you're a student here, just think of your own careers ahead and how much of the things that you accomplish in life will be at least enabled or propelled in part by computing technology. And it's pretty amazing. And so for my mind, there is no more important thing to study and to develop in this current era of humanity than computing technology. It is the most powerful force for kind of technological democratization that we have right now. And we really have only just begun. We understand so little about the future of computing technology. So at least for me, I'm just incredibly excited to be involved with this. All right, so I say all of that because in fact, those two things, the moon landing and the mother of all demos, the ARPANET, were very important contributions by a government agency called DARPA, the Defense Advanced Research Project Agency. Actually, ARPA, and they keep deciding whether they want to put defense in front of it or not. So it's sometimes ARPA, sometimes DARPA. And so the Saturn V booster rocket was actually ARPA Order number 1, the very first funded program by DARPA. And then, of course, the ARPANET was a much later investment, but equally amazing for 1969. And so I was at Carnegie Mellon, a very happy professor, ultimately became the department head, which is a very good job at Carnegie Mellon. And then Barack Obama ran for president and got elected. And a friend of mine who I had gotten to know when I was a vice provost for research at Carnegie Mellon, because he had been a vice provost at Berkeley, as Tom Khalil. And Tom was appointed by Obama to be the new Science and Technology Policy Director, a position that he still holds in the administration. And so in between the election and the inauguration, Tom Khalil was asking all of his friends to write 2-page white papers to establish new policy in science and technology for the Obama administration. And Tom Khalil asked me to write a 2-pager on DARPA. And he did that because he knew that I had been on an advisory board for DARPA. And the issue here was that DARPA was this storied research agency, invented the ARPANET and led to the internet, invented the field of material science, invented stealth bombers, invented UAVs, created a tremendous amount of technology in advanced prosthetics, and on and on. But after 9/11, President Bush directed DARPA and other agencies to focus exclusively on the global war on terror. And while that was a noble cause and probably justified at the time, it led to nearly a decade of kind of reduced scientific vision and reduced academic investment by DARPA. And so the purpose of this white paper was to try to argue that DARPA should return to its roots under the Obama administration. And so I wrote this. I realized at some point, since I had never worked at DARPA myself, that it wasn't that credible. So I asked my friend Randy Katz, professor of computer science at Berkeley, to join as a co-author. Since he had actually worked at DARPA, I thought that would add a little bit of weight, and we wrote this paper. Well, unfortunately, after this, I really got into trouble. And this paper was used to bludgeon me into leaving my post as head of computer science at Carnegie Mellon and going to DARPA to put this into action. And to this day, I still regret not putting Randy Katz's name first on this paper. My wife, you can imagine the difficult conversation with my wife. She's wondering, what? You are going to move without us? There was never an option of my wife and son moving with me to Washington. And so I ended up going to DARPA. And in fact, it was a very, very difficult thing for me to do. And when I went to DARPA, I had to go back and forth, and about 1 week before I started my job for real at DARPA, it's about a 4-hour drive between Pittsburgh and Arlington, Virginia, where the Pentagon and DARPA are. And I was sitting at home in Pittsburgh, and it's about a week to go before I started my job, and the director of the agency calls me and said, "Peter, you have to come here tomorrow. The Secretary of Defense, Secretary Gates, is coming to DARPA, and you need to tell him what you're going to do." And so I have no idea. I complain, I have no idea. She says, "You have to have this meeting. You can't say no to the Secretary of Defense." So I get in the car, and I'm driving to Washington, and I'm just preoccupied. What the heck am I going to say? And I'm so preoccupied, I cross into the Maryland border and then get pulled over for speeding. And then I'm really worried because I realize I'm going to have to do this drive probably every week, and I don't want to lose my license. And so I arrive in DC, I have lunch with a friend, and I'm complaining about this. I'm complaining about not knowing what to say. I'm about to have a meeting in a few hours with the Secretary of Defense, and then I'm complaining about my speeding ticket. And my friend, whose name is Peter Harsha, who's the policy director at the Computing Research Association, says, "Oh, you should download this app called Trapster." Okay. And so what Trapster does is combines ubiquitous access to the mobile internet, the cloud service of mapping, and the social media of giving you a thumbs up if you see a speed trap and you report it. So as you're driving along, if you see a speed trap, you tap on Trapster and it records that. Or if you're driving along and you see someone else, it beeps at you if you're passing near a place where someone else is seeing a speed trap. And if you actually see the speed trap there, you can give that person a thumbs up and their social status rises. And so it was a great thing, and it really saved me. It saved me not only because I never got another speeding ticket, but it saved me because this is what I talked to Secretary Gates about. So, because what I decided I would tell him is that the world is changing, that there is a convergence of trends in social media, in cloud computing, and in mobile access to networks that are going to converge to create whole new capabilities that could bring new military capabilities as well as new military threats. And then I talked about North Korea Uncovered, which was a crowdsourcing site that has been uncovering a lot of intelligence about things that are going on in North Korea. And Secretary Gates was very fascinated by this, and he asked me to speak about this to a group of 4-star generals. And those 4-star generals liked everything I said, but as soon as I talked about social media, they kicked me out of the room. They were saying, come on, DARPA shall not work on social networking. It's all just silly. It's Friendster and MySpace and Facebook. It's not appropriate for DARPA. And so this brings up a point here, which is a motto that I learned at DARPA, which is that disruptive ideas are fragile and fleeting. It often happens that the most disruptive ideas are the easiest ones to poke holes in when you first hear them. I was actually on the Usenet news group alt.hypertext in 1991 with 241 other subscribers when Tim Berners-Lee announced his World Wide Web project. And I remember thinking, what a simple, stupid idea. And that type of thing happens all the time. And so again, it's very important to try to remain open-minded. You have to be discerning, but also to remain open-minded. And the kind of dismissal of any potential importance of social networking in the military context was also something that was just it was a very easy opinion to have. Well, so I was directed by the DARPA director as my first project at DARPA to prove the military leaders wrong, to prove that social networks could actually be good for something. And so the idea that I came up with was to stage a balloon hunt. And so this was something called the DARPA Network Challenge. We took 10 8-foot red weather balloons and hid them in public but undisclosed locations throughout the United States, moored to the ground and 100 feet in the air, for 8 hours on the 40th anniversary of the first 4 nodes of the ARPANET, and offered a $40,000 prize for the first person or team that could accurately report the location of all 10 balloons. And the idea here was to show that people could use social networks to mobilize the thousands or millions of people necessary to find these 10 balloons, and that they could do it faster than the Navy and Air Force could with their satellite reconnaissance. And so I came up with this idea with a group of people. I was really excited. I went to bed that night, and I woke up, and I realized, oh my God, what am I thinking? I'm just a fuzzy-wuzzy professor. I have no credibility, and my first project at DARPA is to run a balloon hunt using taxpayer money. And so I had a meeting with the DARPA director that morning. I was supposed to report out what the project was that I would run to show the military leaders that social networks are important. I went to her office, and I said, well, we came up with an idea yesterday, but I realized this morning it won't work. I'm going to need a few more days to come up with something better. So she said, well, tell me the idea anyway. So I explained the whole thing, and she said, Peter, wow, that really does sound like a dumb idea. But at DARPA, disruptive ideas are fragile and fleeting. That's the idea you thought was good yesterday. You're going to execute. And so she forced me to do it. And the results were pretty stunning. There were thousands of teams that entered, teams even from Syria, from Iran, from China, from Russia. DARPA servers got hacked so that there were viruses implanted by the Russians, so that when other people got infected and reported balloon sightings, they would go to a spoof website they were running. I mean, it was just a fantastic thing, and the team from MIT found all 10 balloons in less than 9 hours, after having mobilized over 2.5 million people. Pretty amazing. And the day that I got on the airplane to fly from Washington to Seattle to start my job at Microsoft, a crew that had worked on that project with me at DARPA was flying to Afghanistan to take some of the lessons learned in deploying virally information from the US military in that theater of war. So really quite amazing. All right, so with that, I want to now just explain than what is exciting me right now. And there are lots of things, because Microsoft Research is really a wonderful place with so many things going on. But one of the things that really gets me excited right now is the prospect that we're going to get computers to actually see and hear and understand like people do. And when I explain this, I use this image from the Star Trek movie, The Voyage Home. And if you haven't seen this movie, it's not a very good movie, but if you see it, you know, there's a menace that is going to destroy the Earth, and the only way to save the Earth, after some research, is to go back in time, get a humpback whale, and bring it back to the 25th century. And that a whale will be able to talk to this menace and talk it out of destroying the Earth. Seriously, okay. So what they have to do is find a whale. Of course, whales are long extinct in the 25th century, so they have to find a wormhole. They fly the Star Trek Enterprise to the wormhole, go back to modern-day Earth. They land in modern-day San Francisco. The first thing they need to do is find a computer. They run into this office. Unfortunately, all they see is a Macintosh. And we like Macs now at Microsoft, so it's good. And Scotty, the engineer, goes up to program the computer. And what does he do? He talks to the computer. Of course, because if you're in the 25th century, that's what you do. Nothing happens, and he goes, oh, of course, we're in the 20th century. So he realizes his mistake, picks up the mouse, and talks to it. And that's the scene. And it's a funny scene because we have all actually in real life lived with the indignity of performing unnatural acts to use a computer. I mean, think about it. You've all had to train yourself to do that. And so, in fact, a whole thread of research and research investment in Microsoft Research is in what's called natural user interaction. And so what is exciting now is that a huge amount of progress has been made on this using deep neural nets or machine learning. And with deep neural nets, what you do is you take a whole bunch of training data, a whole bunch of waveforms, feed it to a deep neural net, you train the system, and you produce automatically a runtime system that can take speech input and give you the transcript. And the beautiful thing about these deep neural nets is that the more data you give, the more training data you give, the better the speech system is. That has led to an amazing improvement in the performance of these speech systems. So on the y-axis is what's called the error rate. And this is the NIST switchboard test. And so the error rate, roughly speaking, is if you were to write down in real time a transcription of my speech, the number of words wrong, the percentage of words wrong is the error rate. And so you can see in 1993, it's almost 100% wrong, pretty bad. And now, in laboratory conditions, we're below 7%. Much better than any of you could do in real time. The other thing I like to show here is that for a decade, from about 2000 to 2009, there was no discernible practical improvement in speech recognition. And this is a point that I try to explain to managers everywhere. Research is really a long game. It takes a kind of stick-to-itiveness and a commitment. And again, in that period, people can have serious doubts. But every day that you do research in that period, you're learning more. And at some point, you have the chance to pass a tipping point and see the kinds of improvements that we have now. Research is a long game. The other thing about research is that you always get unexpected outcomes from research. So one of the coolest things about these deep neural nets is the following. Let's take our deep neural net that we've trained on English speech, and now let's give it some French. Well, then you get a runtime system that's able to understand both English speech and French speech. But the amazing thing is, by adding French training data to this, the English improves. And now you feed this thing Chinese, and again, the English improves. And the Chinese comprehension is better than if you had started with the fresh neural net. And what we see as we start to uncover the intricacies of what goes on in these neural net structures, we're seeing more and more the possibilities that we can uncover some core internal representations of the structure of human speech. We also have the ability to apply these neural nets to vision problems. And so there's a fun app that we demonstrated a while ago that allows you to ask the Cortana digital assistant, what kind of dog is that? And you point your camera to the dog and it tries to tell you the breed, and it does it remarkably well. And so these outcomes are oftentimes very unanticipated. But coming back to this, it's not only that the Star Trek people could talk to the computers, but if you remember, Star Trek could go all around the universe and talk to anyone in the universe with the help of a universal translator. And given that we have universal translation in text today, and in fact, you can even translate to and from Klingon right now if you use the Bing translator, we can ask, can we put these things together to get real-time speech-to-speech translation? And so one of the things that really has me excited is this possibility. And so let's see if we can get this. Hello.
你好，
I'm really pleased to have this opportunity
我很高兴有这个机会
to show you a little bit about what goes on in our research labs.
给你说说发生在我们的研究实验室。
As you can see, even though I don't speak a second language,
如果你能看到你，即使我不说第二种语言，
I'm speaking to you now in Chinese in my own voice.
我说话，你知道的，中国用自己的声音，
It's pretty cool.
这很酷。
This is all made possible because of the advances in big data and machine learning.
因为在大数据和机器学习的进步，这都是可能的。
The same advances we've been talking about today.
我们一直在谈今天同样的进展。
And while the system isn't perfect,
虽然系统并非完美，
in fact, you can see it's making a few mistakes.
事实上，你可以看到它让几个错误。
The rate of improvement has been rapid.
发展速度很快。
We think it will be practical soon.
我们认为这将很快实用。
We believe the underlying technologies will change the world.
我们认为，基础技术将改变世界。
They will help you become more productive.
它们会帮助你提高生产力。
And they will help you connect with people around the world.
它们会帮助你与世界各地的人联系。
At Microsoft, we dream of a world where language no longer separates us.
在微软，我们的理想世界里，语言不再把我们分开，
but instead brings us closer together.
而是让我们一起更近。
We look forward to all of you joining us in this exciting dream.
我们期待你加入我们在这激动人心的梦想。
Thank you.
谢谢。
So the advances have been just really incredible. And by the way, I always cringe because I know several of you are native Mandarin speakers. And so you're familiar with a couple of relatively embarrassing gaffes. The most embarrassing one, and this is an inside joke for those of you that speak Mandarin, is I once gave a speech with live translation talking about growing up in a small and snowy town in Upper Michigan, and it got translated into Mandarin into a small snow white town in Upper Michigan. If you're a Mandarin speaker, you know how profane that is, and so let me just leave it at that. So now the thing that has me really charged up is the possibility of taking one of our most important products at Microsoft, which is Skype, with 400 million active users and almost 1 trillion minutes of talk time per month, and turning it into a portal to eliminate the language barrier. And so I'm just incredibly excited that next month we will begin the public beta launch of a Skype universal translator, initially focused just on 2 languages, but month by month over the next year we'll be adding more and more languages. And so just imagine, again, the democratizing power of Skype. Skype being completely a symbol of democratized access to global telecommunications, and now making that be a portal for eliminating the language barrier. And so it's something I'm incredibly excited about now. I'll skip all of this because there's all sorts of problems because, of course, when I lecture, it's one kind of speech, but when you talk on Skype, you say very different things, and it can be very, very difficult. The new CEO, Satya Nadella, has been really pushing this, and that's been a very exhilarating and scary thing. It damn well better work next month, and I'll be hiding under my desk when it launches. But the point there is when you change the world, that kind of opportunity happens really very seldom, and it's something that we just have to take, no matter how scary it is. So with that, let me just close by saying thank you all. I could not be more proud of my heritage and my part of being in the University of Michigan family. Seeing all of you just reinforces my pride in being a part of all this. So thank you for having me, and best of luck.
We have time for a couple of questions.
So we have noticed that recently several things happen in Microsoft research. For example, we don't have Silicon Valley research labs, and Microsoft research have been divided into two groups like the MSR labs and MSR Next.
Yes.
So could you please elaborate more on that change, and what's the influence of this change of strategy on the future of Microsoft research?
Yes. So we have a new CEO at Microsoft. In fact, only the third CEO at Microsoft. To think of how remarkable that is. And one of the things that the new CEO is doing is trying to have a restructuring of the company, really formed in an image that will be much more adaptable to the new world. And so to prepare for that, he has asked for an overall reduction of the size of Microsoft by about 20,000 people. And so every single part of Microsoft was asked to participate in the reduction, and that includes Microsoft Research. And so what we tried to do in Microsoft Research was to absolutely minimize the number of people affected. And so, the best way that we felt to do that was to eliminate one of our labs. And so we ended up eliminating one of our small labs, and in fact, one of our smallest, which is the lab in Silicon Valley. And I believe that over the next 2 years, you're going to see a significant growth in all of the engineering teams in Microsoft, including Microsoft Research. And I'm hoping we'll go back to Silicon Valley. It's such an important part of the world. But for us, we were really looking out for our people, and we wanted to have as few people affected as possible. With respect to some of the restructuring of things, one thing that we're trying to do is Satya has given Microsoft Research a new mandate. In the past, under Steve Ballmer, Microsoft Research was not allowed to ship products directly to consumers or to businesses on its own. It had to work with product teams and had to play a supporting role to product groups if it wanted to do that. Microsoft Research has always been able to, and still does, have the ability to just do pure fundamental basic research. But for the people in Microsoft Research who want to do more kind of product or deployment-oriented things, it has been always a little bit difficult because we've always had to work through a product team. Under Satya, Satya has given MSR the license to go directly to market. And that's incredibly exciting. I mean, some of our researchers are just completely thrilled. But it's not a simple thing. You need to develop go-to-market plans, you need some marketing, you need more engineers, you need support structure. There's all sorts of stuff that happens there. And so we've created a new organization called MSR Next to try to provide all of that. And it's already paid off. I was just telling some of the faculty, in China, we just deployed a new product called Xiaowais. Within 72, it's a really engaging AI intelligent chatbot. And within the first 72 hours of the deployment, we got over 10 million users. I think we're almost 40 million users now. Users are on average having over 1,100 conversations with Xiaowais every month. And we're deploying more and more AI. And that deployment is done completely by Microsoft Research. We have a fun, cool little app you should all download on whatever you're using, Android or iPhone or Windows Phone, called Xim, X-I-M, Microsoft Xim. And so it gives you a way to very seamlessly share a bunch of photographs with your friend without having to share your phone. And so that you'll see more and more things like this in this new structure. And it's, for me, managing MSR, I have to constantly remind our researchers that we should be thinking very far ahead. But right now, I will tell you, researchers are just super excited that they have the ability to just go straight out to end users. Yes, in the back.
What are the applications of machine learning in the lab other than Skype?
Machine learning is so pervasive. It's really incredible. One of the largest scale applications of machine learning is in what's called entity extraction. So in the Bing search engine, if you use bing.com, and you all should, when you do a search, if you search for one of your professors, you will see search results in the left pane, but on the right pane, you will see some information, like biographical information and a photograph and collaborators of your professor. That is actually a printout, essentially, of a part of a very large graph with billions of nodes in it called Satori, and it's an entity graph structure that's just extracting more and more information about people, places, and things and events on the web. And so machine learning has been an incredibly powerful tool in getting that information out. If you are a gamer in the Xbox and you use Kinect, of course, all of the computer vision is machine learning powered. If you are playing Halo in an arena, your style of play is being analyzed by machine learning. You're being matched up with other people in the arena through machine learning. And it just goes on and on. Even when you are using Windows, you might notice, if you're using Windows 8 or 8.1, that over time, apps seem to launch faster and faster. Machine learning is actually learning your habits and behaviors in Windows and is preloading applications over time. And so it's pretty pervasive. Yes?
For the language processor, why is it that when you add French, it turns to English instead?
Yeah, this is one of the great mysteries. And it's very seductive to believe that there's something brain-like going on, although I think that's not true. But if you think about, I don't know if you've had to learn a second language, but you probably learned that second language faster than your first one. And so one thing that happens is that in these layered neural nets, the filters that are learned in the lower layers of these neural nets seem to be very common across multiple languages, across Mandarin, French, Italian, English, and so on. And so every new training set, no matter what language you get, seems to refine the quality of those filters. And that it's only the very last layer of the neural net that is highly specific to one language. And so it's sort of like, again, you need to be careful because it's probably not like this exactly, but it's seductive to think that in the same way that you learn the parts of speech, nouns, verbs, you learn about what is a syllable, you learn about accents, and those things apply to every language. There's something that seems analogous going on in the training of these speech engines.
No more
Am I off the hook?
Not quite. We have a small token of our appreciation for a great talk, and more so for a remarkable career that reflects on Michigan. Let me see what's in the bag.
All right.
Wait, there's more. Open carefully, because
Okay.
I don't know what's in there.
Ah. All right.
Wait, there's more. Now here we really need to be careful. You can still open it, but be careful. So this is one of the tubes in the original ENIAC.
Wow, that's
It's
amazing.
signed by Art Berks, the founder of the CS program. And it's one of the 25 units that we have. So one of them is we entrusted on you, Peter.
I'm really touched, and I actually still remember with fondness taking the history of computing course from Art Berks, and so really one of my favorite courses of all time. So really means a lot. Thank you so much. Thank you all. Yeah. Yeah. That's quite amazing. Well, thank you. Great.
Thank you.
Thank you.
Have a fun and safe Halloween. Thank you. This was great.
Yeah, that's amazing.